And I am Senegaglia. I will present to you today work about the cyclic elastic loading behavior in pre-stained lattice structures. And this work is about my research group that is searching about lattice structure and in the big picture of PNRR development of an Italian government funding. So the agenda was about a little bit of introduction about lattice structure, then how we set up the DIC and the phi model for understanding the readings. Then we discuss about the compression test that we performed with those kind of structures, data post-processing, and some conclusions. So why we choose the triply periodic minimal surfaces? Because they are complicated. As you can see, also for the animation, those kind of lattice structures based on surfaces. So we can avoid some little inconvenience about starting of the lattices, but in exchange of very hard complexity of simulation and measurement, as you will see soon. Those are the parameters for those kind of lattice, and this structure is designed by ourselves with our custom metal-based code. This kind of structure are very common in a lot of multi-physics application. Also a lot of structures, and in particular the gyroid one. Those are some kind of application that you can use it, but in this work we want to explore what they can do in a very strained and stressed condition. As you can see, the big picture about metamaterials are considering all this mess a sort of material, but for a uniaxial loading, you can see a very different stress concentration, distribution, everything. So we want to know if this behavior is obviously a disadvantage, but can be also used for something. Our approach is to test a specimen to investigate through affordable procedures, and then if the results are convincing, try to make an assessment about this behavior. The fact is, this localized stress can be seen as a plastic joint, and then have an elastic global behavior and a local plastic behavior that can be useful for something, as you will see in the conclusion, obviously. So the point is simulate those kind of things and also observe it in some way, but with the field and not for a point value. So the DIC was fundamental for that. As you can see, we use a shell-based model instead of solid model because plasticity in nonlinearity in those kind of structures can be very difficult to handle. But we use periodic boundary conditions for helping the convergence of those models. So in using those kind of conditions, we assume that the material is sufficiently similar to a true material, and then simulate a short portion of the specimen to understand better its behavior. As you can see, is second order formulation, because for plasticity can be helpful. This is our setup. As you can see, we have an external sense of displacement for future-proofing behavior for having a lot of those specimens tested, and then we don't have to remove the sensor and reapply it, giving some bias to the formulation. We also have our DIC camera that have a very high resolution but low frame rate for bandwidth reasons. And we have also the testing machine, obviously, that is in controlled in load. So we can assess better the hysteresis of our specimen. So the external sensor can be useful for handling more specimen, but in our case can be a little bit tricky because we have to handle the stiffness of the clevis. So we handle it with this because obviously we have also the load registered by the machine. So we applied a very easy correction, so our results are more accurate to the AC measurements. It's worth to notice in the previous slide that we cannot apply it directly to the lattice because we don't know the distribution of the area. So the stress and how the load is managed by the lattice is a very big problem, as you know. This is what the camera sees in our test. In the IC, we need to set a sort of step in terms of pixel for understanding how the algorithm is trying to understand what is seen, basically. We use a lot of steps for understanding what step is the most accurate one for our reason. The meaning of best will be shown shortly. And then this is a technicism about the IC. We also made a study about the subset ranges for having the best possible combination of parameters for an intensive experimental campaign. So we have our specimen. As you can see, is for compression. Obviously, we don't have any kind of comfort zone for the testing machine, but we have a base that is very useful for having a conformal contact in one of the part of the specimen and the decent alignment for the machine. The materials is alloy 718. The specimen was produced by ourselves and with this machine that is very powerful with those brief information. And that is our final specimen. With obviously we need the removal of the supporting material and then post work for the aligning process. This picture is useful because I suggest you the building direction. So this is the load versus time curve that we explore. As you can see, we always made a pre-stress condition before the loading cycle, that are those ones. Maybe it's better that. And in blue, we have our acquisition with the IC. Those are a lot of data. I'm sorry that those kind of cycles are so short. We want to have more cycles for a better understanding, but the amount of pictures is insane. So this is a little zoom on our cycles, and we have 10 cycles to understand at least if we have an evolution of the response or the things remain the same. In all cases, we have the same behavior for the first cycle up to the last. So we apply our correction. That is quite straightforward. So we encountered the first problem. This kind of structure, we can see through the specimen, we can see the wall behind. So for a method that based on the picture that you can see can be tricky. So our idea is having a sort of threshold of what we cannot see, obviously, through the wall behind the specimen. And after this preliminary threshold, we applied the DIC reading that is quite useful because in the first process, we can remove it. In fact, we have a theoretical 7.3%, 0.07% of unreadable area. That obviously, for perspective reasons, cannot be the same in a real picture. So we have 2%. And then in the IC, we have similar values that are biased by the fact that it tries to search in the search area, so it's a little bit higher. But at least we can avoid those kind of lectures that basically makes a lot of noise for nothing. So this is our first investigation about the step. So we plot the elastic microcycle that I showed you before versus the step. This is it's an error, it's the step. And as you can see, the standard error that I will introduce you what it is basically more or less the same in every condition instead of a very finer step in the IC. So we decided to take the averaged minimum one that is not so different by other ones, but it is a starting point. So we have the same grid for every microcycle that can be very useful for a lot of specimen. This is for the sub-step optimization. As you can see, we have a standard error of between 2.6 up to 2.1 micrometers. And this standard error is calculated by the elastic loading of the elastic curve, as you can see in a moment. Also, the grid correlation is quite stable. So what is the standard value that I will show you? I have shown you before. We have the signal of the machine that is not aligned to the signal of the DIC. The signal of the machine is one, maybe it's better, is the violet one, and the DIC is the blue one. So we made an interpolation by sinusoidal curve, and then we align it. This error is standard deviation is our goal for the minimization of the parameters of the DIC. So this is our reading. As you can see, is very stable. Is clear also how the deformation evolving into such a complex structure. As you can see, the maximum to the minimum is 16 micrometers to up to plus 16 micrometers. That's a clear picture of that. As you can see, the distribution of the displacement is not linear, but with our DIC, we can at most try to catch this kind of nonlinearity. As you can see, also there is a lot of scatters that depends on the layers of the printing, and this for us can be an advantage, but in reality is not advantage. It's not simulating the dots on a DIC normal reading. So this is the strain. As you can see, it's very noisy for that reason, but if the animation works, okay, we can at most recognize some of the area where the strain is maximum due to the fact that the strain is localized. But this is the proof about the fact that we can tune those kind of plastic joints for having a different result. In fact, in the final curve that we obtained, we observe that in those elastic cycles that are elastic because the scatter is minimum. I don't put the standard deviation because it is insanely low. But as you can see, from the first cycle that is the most in the left to the last one that is the most in the opposite, the most in the left, as you can see, we have a stiffening of the structure that it remains in the structure also after the final loading. In fact, we have a first effect and the first plastic damage accumulation where the elastic modulus, loading elastic modulus, grows up to 10% and then remains stable after also a very, very plastic strain applied to the structure. So in conclusion, we have demonstrated that those kind of structure is based on bending flexor behavior and not on stretch as literature has demonstrated in a lot of papers. We shown also this kind of permanent stiffening effect. It can be very useful for tuning also the final properties of the structure. And we shown a systematic approach on the AC and try to understand the strain field of those kind of structure. In the future, we can use a solid model, a better DAC, and a standard approach to try to have a curve that predicts also the stiffening effect. Thank you very much.